Okay, hello everyone, and welcome to the August A3D3 seminar. So we're starting our second chunk of 6 months. Again, going back to one seminar for the next 4 months, which are going to be covering our 4 pillars, and then we'll have a general one and then a distinguished speaker one at the end of that 6-month period, which I think takes us to January. So I'm very pleased today to introduce our speaker, Ben Nachman. He's a staff scientist in the physics division at LBNL, where he's also group leader for the machine learning for fundamental physics group. He was a Churchill Scholar at Cambridge University, and then he's got his PhD and PhD minor in statistics from Stanford. Is a Chamberlain Fellow in the physics division at Berkeley Lab, and he's particularly interested in developing, adapting, and deploying machine learning algorithms to enhance data analysis in high energy physics, which I think is a subject that's very close to many of our hearts and many of our interests. Ben's going to be talking to us today about I'm blanking. Outlier anomaly detection type material. Ben, thank you very much.
All right. Can you confirm you can hear me?
Yes.
Great. Thanks so much.
And we can see your slides.
Great. Let me put it in full screen, and there should be in full screen. Good. All right. Well, thanks so much for the invitation to speak. And today I'm going to tell you about anomaly detection, and in particular, how we can move towards online anomaly detection for particle physics, which I think will be of particular interest to all of you. All right, so first, because I understand that not all of you are high-energy physicists, although I see many familiar faces in the audience, let me first tell you what I mean by particle physics. And it will be a subject defined by the questions. And in particular, there are important theoretical and experimental questions that motivate a deep exploration of the fundamental structure of nature, and that's what defines particle physics. On the theoretical side, there are key questions like, why is the Higgs boson so light? The Higgs boson was discovered about 10 years ago, almost exactly 10 years ago. And it was predicted by the standard model of particle physics, but its mass is in kind of a weird place that it's hard for us to explain from more basic principles. There are other questions, like for instance, why do neutrons have no dipole moment? And if you don't know what a dipole moment is or don't remember what a dipole moment is, more or less, if you Google a picture of what a neutron looks like, you'll probably get the left-hand picture, a nice circle with 3 dots. Those balls correspond to the quarks inside the neutron, which are 2 down quarks and an up quark, and probably they're arranged in a nice triangle. But it turns out that actually the neutron is not arranged like that. It's more like in a line, and we don't really understand why. Okay, there are other questions for which there's a observational motivation, so in particular dark matter. Perhaps you've heard that most of everything is made of dark matter. I mean, most of the things around you are made of visible matter, but most of the energy density in the universe is dark matter, which was discovered through astrophysical observations that we don't really know what it's made out of. And there are other questions like why do neutrinos have a mass? Neutrinos are fundamental particles that are like electrons, but they have no electric charge, and their mass is very small, but not exactly 0, which is not explained by the standard model. Okay, so we have all these questions, and there are a number of puzzles which have impelled us to perform thousands of hypothesis tests, and so far we have found no significant evidence for physics beyond the standard model of particle physics, which is sort of our theory of everything. So this leaves sort of 3 possibilities. One, there's nothing new at accessible energies. The other is that we have to just wait, and the third is that we're not looking in the right place. Okay, so this last one is what keeps me up at night and will be the motivation for the rest of this presentation. Okay, so there's sort of 2 complementary paths forward. So one is to go and look in many different places, identify specific, well-motivated places, and go look to see if there's something new there. And the complement to that, which will be the focus of today's talk, is to try to look in many places all at once. And there's no free lunch. These 2 methods are truly complementary because clearly for any specific model, if you look for that model, it will be better, should be better, or you're doing a bad job, than if you look everywhere all at once. And so we really need both search paradigms in order to be broadly and deeply sensitive to new physics. Okay, so why not just look everywhere? Well, first of all, there are a lot of places to look. Here is a table. There are a lot of symbols in this table, so I'm gonna apologize for that, and I'll explain a bit what they mean. So imagine that we're looking for a new particle, the A particle, and it decays into some other particles, the B and the C particles. And the point of this table is the headings on the X and Y axes basically corresponds to what the final particles would be. So if the B particle is a standard model particle like a electron, a muon, etc., or the C particle is same thing. And the different symbols in the middle correspond to different models, physics models that motivate this particular signature. So basically every signature is motivated by some well constructed model. And the complement to this is that in addition to there being lots of places to look, most of those places have not been looked at. So this is a similar table where if there's a circle with a line through it, that means that there's no measurement at the moment that tries to probe that region of the phase space. And if you see a number, it's a citation to a paper. And so basically most of the area is uncovered. And so we just don't have the bandwidth to look everywhere. Okay, so a lot of places to look. Also, even if you did look everywhere, you would find a lot of stuff. And you may not may not be what you want to find. In particular, you'll find a lot of excesses. So we need to cast a wide net in a smart way. And that brings me to today's talk. So I want to tell you how we can cast a wide net in an effective way in order to be broadly sensitive. So first, I'll describe the landscape of model dependence and how that's related to anomaly detection. I'll give you an overview of some new ideas, connecting the machine learning supervision with the underlying physics assumption. I'll give a specific example for resonant anomaly detection. In the last part of my talk, I'll discuss how we can move towards online anomaly detection. And just to be totally clear here, when I say anomaly, I really mean unanticipated new physics. So really, the whole search program in particle physics is anomaly detection in a sense, but here I really mean trying to not be as model agnostic as possible, so not positing a specific signature. Okay, so here's the landscape of model dependence. Suppose you want to search for a new signal process. There's sort of two aspects. One is that we need to achieve signal sensitivity. So we want to be able to enhance the presence of a signal if it exists. And this step of the analysis can be dependent on both what the signal is, as well as what you assume the background is, the known physics. And so a given method will live somewhere in this plane where it'll have some dependence on the signal model assumed, as well as some dependence on the background model assumed. Okay, in addition to being signal sensitive, we also have to know what is the size of our background. So this would be like knowing the noise or calibrating the known physics, because we're trying to look for deviations from the known physics. So the known physics here is a standard model, particle physics. And so for background specificity, which is this background estimation, it also will depend on what you assume the signal will look like, and as well as what the background structure is. So a given complete strategy will be basically a point on the left-hand side and a point on the right-hand side. Okay, so let me start with the left-hand side and describe where different approaches live in this space. So most searches at the Large Hadron Collider and elsewhere live in the bottom left-hand part. So basically, you posit a particular signal model and you simulate what that signal model would look like in the detector. You simulate the background model in the detector, and you train a classifier to distinguish the signal from the background. And train here is in quotes because even most of the time, although this is changing very rapidly, it's not training in the sense of a machine learning algorithm, but simply optimizing by hand some selections to enhance the presence of some signal. And so these approaches are basically as signal model dependent and background model dependent as you can get. So they live in the bottom left-hand side. Okay, and with a number of approaches that live away from there. So one would be the top left, where you know exactly what you're looking for. So you can simulate the signal very well, but you don't have a good way of simulating the background. So here would be like signal simulation, training a model to distinguish signal simulation from calibration data that's known to be background. So this is a standard approach when the signal is clean and well understood. So for instance, in a variety of searches that involve Higgs bosons, decaying into photons. That case, we know extremely well how to simulate Higgs decay into photons, but the continuum diphoton background is much more complicated. It has multiple components, and it's hard to simulate. And so we can draw directly from data. Okay, the complement of that is if you know exactly what the background looks like, but you don't know what the signal model is. And so here, this bottom right-hand part would be training a classifier to distinguish data from background-only simulation. And so the idea is if your background model is exactly correct, deviations from the background-only hypothesis would be some indication of new physics in sort of a very signal model independent way. And so it allows you to very generally look for any kind of new physics. Of course, this depends very strongly on the background model. And if your background simulation is not exactly correct, you'll just find all the problems with your background model. This strategy does have some history, although not in the context of machine learning. Strategies that use this approach based on machine learning are quite recent. Okay, so what I really want to focus on though is in this top right part, where there are many new ideas that use modern machine learning, and the goal is to directly learn from data, injecting as little bias as possible on both what the signal model would look like, as well as what the background model needs to be. Okay, so now that's the signal sensitivity part of the story. Now let's talk about the background specificity. So there are also a number of strategies that live somewhere in this plane. The core idea basically is that you want to create a reference. So you want to see if the target and the reference are the same. If yes, you can set some limits on the presence of new physics, and if not, you can declare discovery. Okay, so the most straightforward approach and most flexible, if it's possible, is that you can directly use simulations to predict the background. So this doesn't depend at all on what the signal model is. If you can just simulate directly the background, you don't have to make any assumptions what the signal model is. Almost no searches at the LHC are of this type because the simulations are almost never good enough to take them exactly as they are. We almost have to inject some information from data, but there are some cases where this is known. For instance, you have 4 electrons or muons in the final state. This process is known exquisitely and can be simulated very precisely, and so it's used basically out of the box. Okay, another approach is to use simulations directly, but to constrain the signal sensitive regions with background dominated regions. So basically using simulation only to transfer information from some calibration sample to a signal sensitive sample. So this is what we'll call a control region method, where the control region is this background dominated region. And this is by far the most widely used approach for searches at the Large Hadron Collider and elsewhere. Okay, then there are other methods which are like control region methods, but instead of using the simulation to transfer from the calibration sample to the data, use the data itself. And the way this works is basically if you have 2 orthogonal directions, you can play those directions off each other in order to estimate what the background density should be in the signal sensitive region. And I'll come back to this method later in the talk. Okay, and the most restrictive one, the one that requires the most knowledge about what the signal looks like, is a bump hunt. And I'll come back to this in just a second. But basically, a bump hunt requires that the signal, if it exists, is resonant, and you know the resonant direction. So you're going to fit basically literally a bump. So you have to know. You don't have to know too much about the signal, but you have to know that it's resonant. In contrast, you basically have to know nothing about the background model. You can just fit it directly from data. And so this is really why the background methods live on this kind of diagonal, whereas the signal sensitive ones kind of scatter all across the plane. Okay, so here's just my summary of this first part of the talk about the different methods and where they exist. Okay, so next I want to talk about new ideas. I like to categorize the new ideas based on how the assumption about the new physics, the BSM stands for beyond the standard model, that's the new physics. So you can, once you make some assumption about the new physics, you can relate that to a given machine learning method, in particular, how that method is supervised. So here there are different words, so unsupervised all the way to supervised, and I'm going to walk through each of these one at a time. A machine learning method is supervised if it has full label information, and this is basically most of the time you do machine learning. Most of the time, you train some model, whether it's a classifier or regressor, where every example you present has a known label. So if it's classification, it'll be, if it's binary classification, it'll be a label of 1 for signal, 0 for background. And if it's regression, you'll have some continuous label. And then there are unsupervised is the opposite. You have no labels. And I'll say what that means in just a second. And then there's a whole spectrum in between. Okay, So for unsupervised, there's no labels. And typically the goal of these methods is to look for events with low background density. So in particular, the assumption here is that if the new physics exists, it will be rare. And so under the background only hypothesis, we're looking for events that have a low density. Excuse me. And there are a number of strategies to look for events with low density, and they vary in exactly how they do this. Some implicitly or explicitly try to learn the density. One very common approach that's been well studied is the autoencoder. And the autoencoder takes examples, it learns to compress them and then uncompress them. So there's an encoder and a decoder network. And the loss function, how this method is trained, is basically you want the encoded and the decoded example to be similar to the original example. So that's what it means to be unsupervised. I'm not telling what the label is if it's signal or background. I'm just saying I want you to encode and the decode to be the same as the original. And the point is that if this compression algorithm is doing its job, then it should allocate high capacity to very probable examples. And so if you look for events that are poorly reconstructed from this autoencoded composition of networks, then probably it has low density. And so in this way, it's sort of an implicit density estimator. Okay, then there's weakly supervised. So weakly supervised here, I'm going to mean noisy labels. So every example has a label, but the label is noisy. And the goal of these methods is typically to look for events with a high likelihood ratio. And so the idea is that you have two samples, a reference and a target, and the target will be signal enriched and the reference will be signal depleted. And so it's like the picture that's shown here. You have your signal enriched region, your signal depleted region, and you don't get to observe the color or label on any of these balls, but you get to observe all sorts of other attributes. And you could assign labels. Let's say you call everything on the left a label of 1 and everything on the right a label of 0. So those labels are noisy in the sense that for every specific example, it's not exactly correct, but they are sort of correct with some noise. And so here you can imagine constructing classifiers that try to look for a high probability of being signal enriched relative to the signal depleted region. Okay, then there's semi-supervised, and here I'm going to mean partial labels. Typically, these methods use some signal simulations to build signal sensitivity. So, for example, you could imagine training a classifier to distinguish like a concoction of the full standard model of particle physics against some set of potential signal models. And then the hope is that if you're sensitive to some signal models, you'll be sensitive to other signal models that are kind of close in signal model space, whatever that means. Okay, I'm not going to spend too much time talking about semi-supervised methods in this talk. So now let me just give you an overview of the ideas. I'm going to compare directly unsupervised and weakly supervised. So the top row is the BSM assumption. So the physics assumption for unsupervised methods is that if the signal exists, it's rare, so low density. Whereas for weakly supervised, the idea is that the physics assumption is that the signal is overdense. So it has a high density relative to the standard model. Okay, so the main drawback of unsupervised methods is that rare, that is to say low density, is not coordinate invariant. So if I change my coordinates because of the Jacobian and the change of variables transformation formula, the density will change. And so this is not, this doesn't mean it's not a useful notion, but low density, densities themselves, of course, have units. So it's one has to be careful what you mean. And also unsupervised methods don't improve if there's more signal. So if I have more and more signal, unsupervised methods are basically don't get better. They also don't get worse if you reduce the amount of signal, which is also a benefit. For weakly supervised methods, the main drawback is that you need two samples. You need a reference and a target. And the likelihood ratio is invariant and recorded transformation, so that's the benefit. But you need to have the two. And it does improve if you add more signal because the target has signal. So if you add more signal, it will be better. Okay. So the canonical example of a weakly supervised approach is a resonant search. So I'm going to now spend a few minutes walking through what a resonant search would look like. Okay, so resonant anomaly. So this is a relatively general, powerful assumption, which is that the anomaly, if it exists, is localized somewhere in the phase space, and you know where it is. In particular, here I've drawn it as a histogram where you can see on the x-axis is some dimension. I call it mres because it's going to be suggestive that m is going to be some mass-like variable, and the y-axis is counts. And the idea is that if the signal exists, it's localized somewhere. I don't actually have to know where it's localized because I'm going to eventually scan the location, but I do have to know that this mres dimension is the one where it would be localized. And then the background is just some featureless distribution. It could be steeply falling or whatever, but the point is that it has no features in the range that we're trying to explore. So this assumption is generically true when there are some new particles, and the new particles have a well-defined mass. The point is that the mass will be, the particles will be resonant at the mass of the particle, mres. Okay. So how will we do weakly supervised learning? The first thing we need to do is generate some noisy labels. And so one thing we can do is we can create a signal region, which is basically an interval of mres near where the signal would be, and then a region very close by that would be where the signal is not. And so this will allow us to construct our signal enriched, which is the target, and the signal depleted samples, which is the reference. And this will allow us to generate our noisy labels. And then we can use whatever other dimensions we have available to us to train our weakly supervised classifier. So here it's shown as a one-dimensional space, this X, but in principle it can be many-dimensional. So it could be 1, 2, 3, a few, dozen, 10, 100, 1,000, a million. And so the idea is we can use all these other features to then enhance the presence of the signal. And the goal is that we learn a classifier, we apply a threshold cut on the classifier, so we keep only examples that pass a cut on the classifier, so that the number of background events decreases. And the hope is that you see a bump, basically, and the bump would be the presence, indicate the presence of a signal. Now, there's some interesting questions about what does the classifier do to the background shape, and that's a talk for another time where I can talk about this idea of decorrelation, but I'm going to assume that that's not a problem right now. Okay, so let me give you a very specific example. This picture on the left is a cross-section of the Atlas detector, where you're seeing the proton-proton collisions coming into and out of the page, and this is a section transverse to the collisions in the center of the detector, where the collision debris fly out in all directions. There are these lines in the middle of the detector, which are the bending trajectory of charged particles immersed inside a magnetic field, and then there are yellow blobs inside calorimeter detectors. There's a green one and a red one, which correspond to an electromagnetic and hadronic calorimeter. And then these blue rectangles on the outside are another tracking system that is designed to capture muons. And basically, when you produce very high energy quarks and gluons, they result in these sprays of particles known as jets. And you can see very clearly on this left-hand side these two jets. There's a red jet and a green jet, colored just for visualization. The jets don't have a color. And this kind of topology is indicative of the particle production that's sort of indicated on the right. So imagine you have some new particle, a very massive particle, the famous (1) particle, and it decays into two other lighter particles, the (2) and (3) particle. And those particles, they produce quarks and gluons and other particles that result in these jets. And if there's a mass hierarchy between the 2, 3, and 1 particles, then the decay products of the 2 and 3 particles will be collimated and will be traveling in a localized region of the detector. And so that's what results in these jets. And the idea is that we can use the invariant mass of the two jets as a resonant feature, because if the (1) particle exists, then the invariant mass of the two jets should be close to the mass of the particle. And then we can use all the properties of the jets themselves, the radiation pattern within those jets, as features to do our machine learning. And you can just look at these pictures by eye. For instance, in the green jet, you see these two yellow blobs that are separated by some distance, which is suggestive of some two-pronged substructure that might be the result of some non-trivial decays inside this jet that you might be able to capture. Okay, so this method was proposed some years ago and has been recently applied to data. So the Atlas collaboration at the LHC recently did this measurement where they did a simplified version. So basically the features that were used for the machine learning were two-dimensional, so you can visualize it. And so it was the invariant mass of the two jets is the resonant feature, and then the mass of each individual jet is used to train the classifier. And so you can see on this picture on the top left shows basically the neural network output as a function of the mass of the two jets. And the point is that a signal has been injected at the point indicated by a green cross, and the neural network has automatically identified that there's something weird going on there, and that's why the color is red. actually, it's the neural network output, but it's basically the inverse. It's sort of rescaled such that low values correspond to high neural network score. So it's really identified this region of phase space, something weird is happening. So there's nothing, in the absence of injecting a signal, there was nothing significant found, but this approach already, even though it's low dimensional, has extended the reach of previous searches. And so this is really exciting, and there's going to be, for sure, a continued program of measurements like this going forward. Okay. So while powerful, the approach I've just described doesn't have a direct analog for running online. So basically everything I've said so far is offline. I want to spend the next 15 or so minutes talking about how we can do online anomaly detection. And when I'm talking about offline anomaly detection at this point, I would spend the next 15 minutes talking about extensions to the idea I just told you about, and how those extensions have solved some key problems, have introduced some new challenges, and how there's a lot of many methods are being proposed to gain broad coverage. I think that's a really exciting thing to talk about, but I want to focus for the rest of this talk about how we can move online. Okay, so the main motivation is that if we don't save the anomalies for offline processing, we may lose them before we even begin. And so just to put that in some context, the experiments at the LHC, they have a trigger system that throws away most of the data in real time. And so there's a hardware trigger and a software trigger, which basically in real time, before any events are stored for offline processing, very quickly these systems have to decide if a collision event is saved or not, and then if it's not, it's tossed, and so you never got to look at it again. And so this is a real challenge. So the methods I just told you about, they do anomaly detection offline. So if you've already saved the events, but if you haven't even saved the events to begin with, then there's no chance you'll be able to find the new physics. And so this is the real challenge. Can we imagine doing an anomaly detection procedure online? And one way of thinking about that is, can we design a system that can save events for further processing that are likely to be anomalous? Okay. So most proposals for online anomaly detection, and there have been a few, are a variation of the following. So first is train some unsupervised model, which could be an autoencoder or similar. And I put the word somewhere in parentheses because it's not totally clear where you would train that model. It could be trained on simulation. It could be trained on data that's already been collected. It doesn't really matter, because the point is that autoencoders or other unsupervised methods, they don't necessarily get better for anomaly detection if you add more data. Of course, they'll be better at doing density estimation if you add more data, but density estimation and anomaly detection aren't always aligned. Okay, so then once you have your anomaly detector, your unsupervised model, it's just a function. So you could save the most anomalous events according to their score under the unsupervised model. And so you can save the rarest events in that context, basically as many events as bandwidth allows, which wouldn't be very many. But you can, in this way, save just the anomalous ones. And then I would say the point number 3 is the real kicker, which is that what do you do with the anomalous events once you save them? So I would say this is the part where existing proposals are a little bit weaker. And in particular, I've heard things like give the events to a theorist, look at them by eye, or compare to a simulation. And yeah, each one of these is a challenge, I would say. So 1 and 2, there's nothing, inherently wrong with them. But yeah, 3, I think, is a little bit problematic. In particular, I'm not sure what you would do with the most anomalous events if I just gave them to you. So even like an extremely well-trained 100 physicists, we're talking, no one can look at a single event and tell what happened. And the kinds of anomalies that we're typically looking for are such that the standard model background is not 0. And so it's only in context that you can tell if something is anomalous, and no one example will look particularly anomalous. And so that's why looking at a particular event by eye, unless it's incredibly, incredibly nuts, and even then it may not be obviously strange, because the standard model of particle physics is very generous, and it has extremely long tails and produces all sorts of crazy things. And so the craziest things will be the standard model, and you have to be able to know, is it the standard model or not? And so we really need methods that can achieve signal sensitivity and also provide context online. And so that's the that's what I want to talk about now for a few minutes. Can we achieve that? Okay. So let me talk now about doing unsupervised learning online and also providing context. So if we can achieve can we achieve signal sensitivity and estimate the background all in one go? And I'm going to propose now one solution to that problem. For sure, it's not unique, but at least it's a partial solution. And so the idea is to train not one, but two autoencoders at the same time. So this is sort of a schematic diagram of how that looks like, and I'm going to walk through each of these pieces one at a time. So let me start with the top part. So the idea is that you can train two autoencoders, and here I'm also going to be vague about where you train. It could be trained on simulation, could be trained on data you've already collected. It doesn't really matter. But you see the loss function here has three terms. So there are four neural networks, F1, F2, G1, G2. Why are there four? Because there's two encoders and two decoders. So the G's are the encoders and the F's are the decoders. Okay, and so the first two terms are the usual reconstruction losses. So R1 and R2, they look like this equation in gray, which is that f of g of x better be close to x. So once you encode and then decode, that should be close to the original. And R1 is for F1 and G1, and R2 is for F2 and G2. And so those two autoencoders contribute a loss, which is their mean squared error. We just add them. And then the magic comes in the third term. So the third term has a hyperparameter lambda, which is tunable. And then it takes as input the two reconstruction losses, and it has this thing called disco. So disco is sort of like the correlation. So you could imagine just sticking in the correlation coefficient here. So say like I want R1 and R2 to be decorrelated from each other. If you minimize this loss and that term was the correlation, it would try to force the two reconstruction losses to be decorrelated. And the reason it's called disco is because this is the distance correlation, which is sort of a generalization of the regular correlation coefficient that can include some nonlinear effects. So in particular, here's some pictures from Wikipedia. The top left is probably familiar to many of you, which shows the linear correlation coefficient. It has the usual structure. As it becomes more linear, it gets close to 1. When there's sort of a blob, you get 0. But the last row are pathological examples where even though there's some clear dependence between the x and y axes, the correlation coefficient is exactly 0. In contrast, the distance correlation, it has similar behavior in the top row. So it looks not unlike the case of the correlation coefficient. It's 1 if they're exactly linear. And these pathological cases that we had for linear correlation coefficient, it's not 0. And so in fact, the distance correlation is 0 if and only if the two features are actually independent. Okay, so that's what this disco is all about. So the first step is we train two autoencoders such that the reconstruction losses are independent. Now, why would I want to do that? And the answer is because I want to use those reconstruction losses to estimate the background. So how does that work? We can do that with a method that's very common in particle physics called the ABCD method, which is basically a class of matrix methods that I mentioned earlier in the talk. So the idea is, imagine I have a plane where I have R1 and R2, these are the reconstruction losses. And if they're independent, then the density of the joint distribution factorizes. So imagine I have 4 regions in this plane, A, B, C, and D. And the point is that I can use the independence of the densities to use the marginals to estimate this top right part. So I can basically use the fact that because they're independent, I can take, for instance, the counts in region D, multiply it by the counts of B over the counts in C, and that will give me the counts in A for the background. And so then once you do that, you can do that basically bin by bin, and then you can estimate what the standard model background would look like using this product formula, and then compare it to the actual data in region A and see if there's any difference. And that's one strategy for doing the anomaly detection. So basically, we achieve signal sensitivity with the autoencoders, and then we use the fact that they're independent in order to estimate the region in A from taking the various projections excluding A. Okay. Right. So let me now show you that this works. So here's basically some diagnostic plots for a realistic particle physics example. The data set itself, there's a link to it at the bottom of my slide. It's a data set prepared specifically for online anomaly detection in the context of particle physics. And there's a tilde in front of the word realistic because there are some, it's a really nice, well-curated data set, but there's some challenges, which I'm happy to go into later if you're curious, but it's kind of technical. So left-hand plot shows that these methods can achieve signal sensitivity. So the x-axis is basically train some classifiers, and then we train these unsupervised methods, and we're going to make threshold cuts on the autoencoder reconstruction loss. So scanning from left to right, we can look at the true positive rate. Those correspond to different thresholds on the autoencoder reconstruction loss. The y-axis tells us how good this is. So this is the SIC, stands for significance improvement characteristic, which is the TPR, or the true positive rate divided by the square root of the false positive rate. And if you're familiar with the signal to noise ratio, SNR, this is basically multiplicative factor by how much the SNR improves. So a value of 1 in the SIC means that there's no, the SNR, whatever SNR you had before is the same one you have now. If it's a value of 2, it doubles. If it's 4, it goes up by a factor of 4, etc. So above 1 is good, and higher is better. And the different colors correspond to different injected signals. So the autoencoder itself doesn't know about the signals. So this just shows the performance you get with different signals. And the solid line is the double autoencoder, and the dashed line is, sorry, the other way around. The solid line is the single autoencoder trained in the usual way, and the dashed line is this double autoencoder. And so the point is that you lose some sensitivity, in part because we're now forcing the two autoencoders to be independent, but it's still sensitive to these signals. And most importantly, on the right, this shows the closure of this ABCD method. So basically, the predicted background over the true background, and it's close to 1. So closer to 1 is better. And basically, for all the signal models, you can see in this case, it's within a percent or so. And the x-axis here is basically the false positive rate. So we're talking very small false positive rates, percent or so. A very high false positive rate gets even better, but we're interested in these kind of small false positive rate regime. Okay. Great, so that's all I wanted to say about this method. This is one potential approach to do unsupervised learning online that also allows us to estimate the background. Okay, so then the last thing I want to talk about is, can we do weakly supervised learning offline? So I basically said earlier this was not possible because you need a reference and a target, but there might be some ways of doing it. And in general, online compatible anomaly detection for any of the methods is active R&D. And I'm just going to give you one possible solution here. It's a little bit crazy, but I think it's a useful approach to think about what could be possible. Okay, so the usual thing we do is, as I said earlier, we develop an anomaly detection trigger. So we make methods that focus on how we would save events to analyze them offline. So in the autoencoder way, we made an autoencoder, we took the reconstruction loss, we made a threshold cut, and we saved events, which we could then process later. And if we saved also context from this, ABCD method, we would then be able to also estimate the background and do a full approach. Okay, but the idea is, what if we don't save individual events? What if instead we basically save all the events all at once, and then analyze them later using some whatever method, unsupervised, weakly supervised, whatever. So what exactly do I mean by that? So imagine I have a full event, no compression, and given event would be many numbers for a single event. This is like what a collision event might look like. You could imagine compressing a single event, which would be saving only a small number of numbers per event, and compressing an entire data set would be, instead, you save a fixed number of numbers for the full data set. So that's these datas. And the point is that if you collect more data, the right-hand side does not grow. It's just fixed depending on how big theta is, whereas as you collect more data, the two left-hand ones, they grow. Okay, so how do we propose to do that? The idea is that we propose to train an online density estimator. So the way this works is you have some collisions, and the usual path is the bottom one, where you have some trigger that decides if you save events or not. And if you save the event, you can process it offline, and you can do some analysis like a bump hunt. Instead, we propose sort of a parallel path, where for every collision, it gets passed to a density estimator, say normalizing flow, which learns to learn the density of the data in real time. And then when you're done taking data, you can generate examples from your normalizing flow and then analyze them offline using whatever method you like a bump hunt. And the idea is that if your normalizing flow is good, basically it will capture all of the data into the parameters of the normalizing flow. And so you essentially compress the data set to however many parameters you have in the neural network. Okay, so said a different way, basically you have your measurement, and then you buffer some events, and then basically that is your batch. So imagine you're training a normalizing flow, and you get to see some batch of events, but only once. So basically, in a normal way you train a neural network, right, you get a pass, you can make multiple passes to the same data set. You have many batches, and each batch is seen many times. But in this online learning, the way it works is that you get to see a batch of events only once, and you discard it. And so you want to learn as much as you can from that batch of events in order to encode all the information that you have about the data. Okay, and so that's the challenge. So the idea is we proposed a new strategy, a variation on training normalizing flows. You can trade them where you only get to see each batch only once. There are a number of tricks that we developed that make this work better, and I'm happy to describe those later, but I don't have time to go into details now. What I will say is that I think many of you are experts in this sort of thing. If you have ideas for how to actually implement such a strategy, I'd be very happy to talk about it. I think that there have been a number of interesting strategies for doing online inference, but here this is online learning, and this could be a fun thing to talk about. Okay. All right, so here, yeah, here's a picture that shows that it works. Basically, on the left-hand side, this is a simple physics-motivated example where there is some signal, and the x-axis is the number of events. So as you add more events, basically you're able to observe that there's higher and higher significance. This is that there's a bigger and bigger deviation from the background only hypothesis. And it's worse than if you knew exactly where the anomaly was. That's the blue. Blue is just the square, just scales like the square root of the number of examples. And the red is a bit worse than that because there's some limitation in the model capacity from the parameterization of the neural network and also its training schedule. But also importantly, on the right-hand side, this is without signal, and without signal, it doesn't find anything. So there's no artifacts from the procedure itself, and if there is something, it's able to find it. And just to be clear, what we do on the left-hand side for the red is after we've collected the data, offline we sample from the normalizing flow, and then we do a bump hunt to see if there's anything that was captured by the normalizing flow. Okay. All right, so that basically brings me to the end of my presentation. I hope it's clear this is an exciting time to work on anomaly detection for the Large Hadron Collider and also beyond. Many of the methods here are general for particle physics and also well beyond particle physics. This is a rapidly growing area with lots of room for innovation, and not just innovation from importing ideas from the broader machine learning community, although that's for sure very important, but also developing new techniques from physicists. And we'll need many approaches to achieve broad coverage. I've mentioned different approaches on the axis of model sensitivity as well as on the level of supervision. And this is especially true for online. If we don't save the events in the first place, we're never going to find the anomalies. And it's really important to design methods that are both signal sensitive as well as being able to analyze them later offline by calibrating the background. And in this talk, I've only mentioned a small number of examples, but if you want to see more about the state of the art, there's a living review of machine learning for particle physics. It's linked at the bottom. There's a whole section on anomaly detection where you can see a large number of papers on the subject. All right, that's it. Thank you very much.
Okay, thanks very much, Ben. Very interesting talk. And we have a nice amount of time for any questions from our audience. So please raise your hands if you have a question for Ben. Lindsay.
There we go. Can you hear me?
Yes.
Yep.
Awesome. Yeah, so I've actually got two questions. The first one is a bit more physics related, and the second one's more technical and how we do things. So yeah, onto the physics related one. I was curious if you had any experience with dealing with anomaly detectors like this when it comes to signals that are more contact interaction or EFT-like, because the rates are still relatively low for anything that's actually interesting. And so that means that your sensitivity in terms of an anomaly detector is almost certainly going to be degraded to things like this. So have you thought any about how to recover that degradation or bridge the gap between resolved resonant or like, sorry, UV complete resonant searches and EFTs or contact interactions. Yeah.
Yeah, that's a great question. Yeah, today in the talk, basically, I focused exclusively on bump hunts. And because there, I know exactly how to estimate the background. But the problem is that more generally, if it's not resonant, I'll go back to my resonant picture just so that everyone knows what I'm talking about. Right. So if it's resonant, I have a lot of handles for estimating the background. And if it's not resonant, it's much harder. Now, it's not impossible. And so let me just go up to an example here. Right, so I have studied this a little bit. So for instance, this is a paper where we looked at a specific example where the background simulation is very well known. So let's say 4 leptons. This is also a place where people do EFT analysis, right? You can also look for resonant signals in this final state, but you can look for non-resonant things also. And here, the strategy of trying to classify or distinguish data from background-only simulation actually works pretty well. And there's some subtleties like how you deal with uncertainties and all that good stuff. Well, there's been a lot of interesting work recently. But that's a strategy that works in that case. And for sure, it gets worse the smaller the cross-section is of the new stuff. But this is one strategy that works. And there have been other proposals for ways of trying to do non-resonant anomaly detection, but it's in general a much harder problem, and I would say kind of wide open.
Okay, cool, thanks. And actually, while you were talking about talking about this one, I think my other question is not actually a good question, so I'll save it and think about it more. So that's it. Thank you.
Other question, Tom.
Yeah, suppose your smooth background has a known resonance in it and you're looking for unknown resonances. Do you have to subtract off the uninteresting one in order to make it smooth, or does your method just let you find all the bumps?
Right, so you're talking about this specific case of like the weakly supervised learning. I mean, in this case, I'll just quickly flash back to it. This case here, there actually are resonant known processes like Z and Higgs, and it's totally fine. But there, you're taking the background; it's a non-resonant background prediction. But yeah, in the bump case, indeed, if there was some anomaly that wasn't an anomaly, it was like part of the standard model. In principle, hopefully you'd be able to find it. And there are a number of strategies. Like, yeah, one possibility is you could subtract it, and there are even machine learning ways of subtracting. Or you could use it as a calibration data set. Now, for this particular search I mentioned here, there are no standard model processes that are relevant. And so there is no resonant known physics in this case. But there are other searches you could do with this methodology where there could be. And indeed, it would be interesting to think about what to do with those, whether to subtract or to use them as a calibration.
Okay, thanks.
Okay, other questions? Mark.
Hi, Ben. Thanks for a nice talk. Yeah, I very much agree with this concept of the fact that we throw away so much data in the collisions, and really we can't, of course, sustain the readout for such the 99%, but we can certainly learn from it and train models. And so I was wondering if you go back to your this you said crazy idea about sort of compressing all the LHC data.
Yeah.
So I guess I would ask a question, maybe, yeah, here. But maybe also in the context of an idea that's like, I don't know, a couple of us kicked around 5, 6 years ago about taking, so let me say the thinking we had and then turn it into a question. So, I mean, one of the places where data is dropped, right, is so we have this, we have a whole bunch of coarse grain detector trigger primitives, like at the L1 trigger. So before we've issued the L1 accept, we have a whole bunch of trigger bits, right, that in some way, in a coarse grain way, actually represents what the detector is seeing in this coarse trigger primitive way. And then we make our L1 decisions based on certain combinations of trigger primitives. But we kicked around this idea a while ago, never really acted much on it aside from talking, of just what if we just train a network to basically learn all the correlations amongst all the trigger primitives, in a way that then you could later do things. I mean, I guess a generative model like you're talking, or just at least then run the standard model through the simulation and see whether there are, correlations amongst the trigger primitives that are, anomalous given what the detector, how the detector should respond to standard model. So at least you would have some device that would learn there. And, there's all kinds of FPGAs around that area, right? So that comes to this question, which is a bit more general than what we were thinking about, having just analyzing the trigger primitives themselves, which is you have this box measurement. And essentially what I think you're trying to do is compress the entire detector, what the detector sees of the collisions. Is that true? And what did you mean? What's actually being measured in what's being compressed? I mean, all of the hundreds of millions of channels of electronics, or what?
Right, yeah, so it's left kind of vague here. You could imagine the simplest version is to run this in the software trigger, where you basically have, where you can basically have like offline-like objects. And so then you could just imagine either saving the full event if you're particularly aggressive, or say you could compress a relatively, a compressed version of the full event, but enough that it's not, you couldn't save every event. An even more exciting thing to do, which is even crazier, is to run this, at level 1 in hardware. And there, you could also imagine using, high-level objects, because there are, of course, also at level 1, things that look like jets and other things. And that would be less aggressive than trying to save, the 100 million readout channels. That would be, but maybe there's a future in which that happens, or it could happen. But for sure, I would say, like, we had sort of a modest vision, which is like, saving a relatively small number, or compressing the event, all the events in a relatively low dimensional space, which low dimensional could mean 100, but not millions or 100 million.
Okay, thanks. Yeah, so sort of you would live at the HLT level of object stage, but one could push this even further up and just use the primitives themselves as I mean, it would be interesting if there are like really non-trivial correlations. I mean, we've essentially deduced what primitive combinations we want to trigger on because we have signatures, but it'd be really interesting to see if there's any anomalous, like if we start recording all the correlations of those bits of the trigger primitives, whether there's actually like interesting correlations that we're not exploiting in the triggerable events, like the ones we're saving, but yet don't look standard model like. So anyway, I was just thinking, because it's like a coarse resolution, it's like, whatever, let's say, I don't know, a couple hundred bits would then get learned on, and we throw all that data away except for certain combinations that we've predetermined. And if there was anomalies there, that might be interesting at the very early stage of the collisions. Something, okay.
Yeah, definitely. And maybe this is a technology that could be used in that way. I mean, the benefit of this kind of approach, if it could work, is that, in principle, it has access to every event, and then you can do whatever you like offline. So you could compare to a simulator, or in this case, you could run some like a bump hunt if it was some resonant thing or whatever. And so because you have access to the full event afterwards. But yeah, indeed, it sounds kind of interesting.
Yeah, thanks.
Okay, any more questions? Okay, well, thank you again, Ben, then, for a very interesting talk. And thank you for everyone for attending. It is August, but it's still good to see a large number of people attending. And so the next talk will be, I think it's the second Monday in September, and it'll be an MMA talk, and we'll have details shortly circulated on that.
Thanks, everyone. Take care.
Thank you.
Thanks, Ben.
Thank you, Ben.
Yeah, bye. Thanks.
Thanks.
Bye.